Hello and welcome back, everybody. Today in calculus, we're going to be talking about how to create a power series out of a function that you are given, or to be more specifically, it's called a Taylor series and also a Maclaurin series. So that is going to be this section. So the question again, is if I give you a function, is it possible to write it as a power series? So then that way we can utilize all the fun things that comes along with it, like say finding out what is the derivative or area under the curve a lot easier because, well, it's easier to take the derivative or the antiderivative of those type of functions. So here in the first part, we're going to go ahead and derive the Taylor series, as we said. And then in addition to that, we're going to derive the Taylor series for the sine of x then. Okay, so again, Taylor series is just a name for the power series thing that we've been doing so far. So as a recap, just to kind of get you on the same page as as what's happening right now, we know that 1 over 1 minus x is going to be the same thing as the following power series over here: 1 plus x to the x squared plus x cubed, and so on, which is basically the same thing as the summation of x to the n but it only works for certain only works for certain values of x, and those values are going to be from -1 to 1 exclusive of the values. So you can see on the graph that is on the left hand side over here, the red graph is supposed to be the power series and the blue graph is supposed to be the 1 over 1 minus x. Those two are going to be identical to each other so long as your x value is from -1 to 1. So there is the idea that you can write an equation as a power series. And I want to know, is it possible to write it for other equations? In addition, for something like this, well, what if I want the power series somewhere else outside of -1 and 1? Because that's really restricting. What if I want it to be at, like, say, x is equal to 3 or x is equal to 5 or something like that, right? So the power series is going to be centered not at always 0, but rather maybe at some other value that we want. So that is going to be our question that we're going to propose today, and hopefully we can come up with something like that. Is it possible to have a power series at a different interval so that means that your center is about x equals to a rather than just x is equal to 0? Okay, so here is going to be our derivation for it then. So first off, we're going to go ahead and say that let f of x be a function that can be represented by the power series about x is equal to a. Now, by the formal definition of a power series, and that means that it is equal to the following on the right hand side. So you can see that this is in your series form, where you have a bunch of like x minus a, and then x minus a squared, x minus a cubed, and so on and so on and so on. And for each one of those monomials, you're going to be multiplying by some coefficients: c of 0, c of 1, c of 2, and so on and so on and so on, right? So that's your power series. I want to find an f of x that can be I want to find a way to solve for those constants for each of the functions that we actually have. All right, so here's what we're going to do. We're going to go ahead and start by taking the derivative of this f of x. So my first derivative, if I were to find out what f prime of x is equal to, then according to my power series on the right, the first term is going to vanish out, and all that's left is going to be the second term, the c1. And then afterwards, your third term, well, the 2 goes down, and then c2 is just as is, and then we have x minus a. Then your fourth term now becomes your third term, which will get 3 multiplied by c3 times x minus a raised to the second power. And then writing one more term after that, that is going to be 4 multiplied by c4 multiplied by x minus a raised to the third power, and so on and so on and so on. So I'm just writing enough terms so then that way you can see kind of like a pattern for this. Okay, now that we've taken the first derivative, let's go ahead and keep doing the second derivative just to see what happens then. If I take the second derivative, then according to my power series, the first term c1 is going to go away. The second term is going to be left with 2 times c2, and then we have plus 3 times 2 times c3 multiplied by x minus a, and then the term afterwards will be 4 times 3 times x minus a raised to the second power. So this guy right here is going to be, the derivative will be this piece right here. This piece right here, the derivative will be this piece, and then derivative of this will be this piece, and so on and so on. And I'm going to write one more term just because, we've been doing 5 terms so far. So the next one will most likely be 5 times 4 multiplied by x minus a raised to the third power then. okay? All right. So that's the second derivative. And we'll do this probably like one or two more times because, again, I just want to make sure that we're getting the idea as to what's happening, okay? So let's go ahead and take the third derivative over here. So my third derivative, the first term is going to go away. My second term, its derivative will just be 3 times 2 times C3. And then the third term, its derivative, is 4 times 3 times 2 times x minus a raised to the first power. And then the next term after that, its derivative, is going to be 5 times 4 times 3 multiplied by x minus a, and then that becomes squared. And then the next one afterwards is probably going to be 6 times 5 times 4 multiplied by x minus a raised to the third power. So you can see that the power series is basically being diminished every single time. But because there are infinite number of terms, then that means that we still kind of preserve the exponents in this case. All right, here it is, but one last time over here, and then we can put it all together. Now I'm going to take the fourth derivative over here. So the fourth derivative is just going to be, oh, actually, it seems like I'm missing something. I'm missing all the coefficients for each one, and that is a big boo-boo. So let me go ahead and kind of sneak that in if it's okay with you guys. So let's see, that's C3, and then this guy right here. There should be a C4, right? And then that's x minus a. And then the one afterwards, there is going to be a C5, okay? So multiply by C5, and then we have x minus a squared. And then the one after that is going to be C6, and then multiply by x minus a cubed. So remember, the objective here is to solve for these coefficients that are in front. C naught, C of 0, C of 1, C of 2, C of 3, C of 4, and so on and so on and so on. All right, here's the last time then, okay? First term will go away. The second term, its derivative, that is going to give you 4 times 3 times 2 times, looks like it's going to be C4. And then the next term afterward, its derivative, that is going to be 5 times 4 times 3 times 2 times C5, and then x minus a. And then the next one after that, that's 6 times 5 times 4 times 3 times x minus a raised to the second power. And then if we were to write one more, then that's going to be 7 times 6 times 5 times 4, and then multiply by, and I don't want to forget that part again, over here there should be a C6, and then that means that there should be a C7 over here, and that's going to be x minus a raised to the third, and so on and so on and so on. Okay, so there it goes. So I took the fourth derivative, and now let's think about what we're going to be doing over here then, okay? This is a power series that means that it goes on forever. And I don't really like that fact, because if I want to solve for something, I need these terms to diminish. So you should be thinking to yourself, okay, so for what values of x can I plug in so then that way my power series can be solved for? And that value of x that you should be thinking of is a, because you'll notice that there's a bunch of x minus a in each of the factors. So here's what I mean. Over here on the on the left-hand side, let's go ahead and solve for the following. If I solve for f of a, right, let x equals to a, what's going to be happening is every term after the first one is going to be equal to 0, and all that's left is going to be c of 0 then. Okay, so right there, we solve for the first term of our power series. Now, in the second part, let's go ahead and do the same thing, but this time, let's go ahead and let x is equal to a for f prime. Similarly, if that happens, then what we're left with is just the first term, which is going to be C1, okay? Then in the second derivative, if I let x equals to a, all I'm left with will be 2 times C2, because that's the first term and everything cancels out. Then we have, in the third derivative, we are going to have 3 multiplied by 2 multiplied by c to the third. And then one more time, if I have the fourth derivative at x equals to a, then I am going to have 4 times 3 times 2 times c4. And you'll notice that each one of these, they're actually just factorials, okay? They're actually just factorials. So let me go ahead and now put them on the side over here, horizontally, so you can see how that works out. So c of 0 is equal to f of a. And then c of 1 is equal to f prime of a. And then C of 2 is going to be equal to F prime or F double prime of A divided by 2. And then if I have C3, that is going to be equal to F triple prime of A divided by 3 times 2, which I think I'm going to write as 3 factorial just so that you can see a pattern here. Whereas before it's probably going to be 2 factorial. And then if you want over here, we can write that as 1 factorial, and this is going to be 0 factorial. And then finally C4, going for this part over here. If I divide everything to solve for C4, then that's going to be the 4th derivative at x equals to a, all divided by 4 factorial. So there it goes. Now putting it all together, this is going to be our Taylor series then. So f of x is equal to f of a and then plus f prime of a times x minus a. And then we have plus f double prime of a divided by 2 factorial times x minus a squared. Then we have plus f triple prime of a divided by 3 factorial times x minus a cubed, and so on and so on and so on. So there is your derivation of your Taylor series then, okay? And this goes on forever. So if you were to write this out as a summation of a series, that means we're going to start at n is equal to 0 all the way to infinity. It looks like it's going to be your f of the nth derivative at x equals to a, all divided by the number of times you take derivative. So that's n factorial times x minus a raised to the nth power. So that is your Taylor series, okay? And I'm hoping this right here is going to be kind of like a light bulb revelation moment to you, because if you notice the first 2 terms over here, right? If you notice the first 2 terms of your Taylor series right there, that is just the equation of the tangent line, okay? That's the equation of the tangent line at x equals to a. And so that's the reason why there are some times when you take a calculus course, some people say that they want you to solve for not the tangent line, but rather another name for it is the first degree Taylor polynomial, because that's basically what you have right here. That's the first degree, and this is a Taylor polynomial over here, okay? All right, so there it is. There's the derivation for the Taylor polynomial at x equals to a. And there is another one that is called Maclaurin series or Maclaurin polynomial. So the Maclaurin, okay, Maclaurin is supposed to be the Taylor series at x is equal to 0. So taking all of this, we basically just kind of like, compact it. So then that means that you would get f of 0 and then plus f prime of 0 divided by 1 times x, and then plus f double prime of 0 divided by 2 factorial x squared, and then plus f triple prime of 0 divided by 3 factorial times x cubed, and so on and so on and so on. So the Maclaurin series, once again, is basically just the same thing as the Taylor series, but except it's at x equals 0. So you can basically say that what we have over here, this thing at the very beginning, that's a Maclaurin series because your center is at x is equal to 0 then, okay? All right, so now that we have the Taylor series and also the Maclaurin series, let's go ahead and see if we can solve for some of this stuff over here then, okay? So let's see, here is going to be my first part, okay? So the first one, what I want to do is I want to take that series that I was given right here, which is 1 over 1 minus x. And I want to go ahead and apply the Taylor series to show that it's going to come out to be the same thing. But if you recall, the problem that I had earlier was I want to find the Taylor series, not always at x is equal to 0, but what about if at x is equal to 3? So meaning, if I go back to my curve right here, I want to know what is my Taylor series around x is equal to 3 that's over here, right? So that's going to be my question mark. All right, so let's go ahead and do that then. So first, what I'm going to do is I'm going to go ahead and write it according to what we just what we did. So we have f of x is equal to 1 over 1 minus x. Okay. Now, according to Taylor series, the one that we derive, you're going to have to solve for the derivative at that point where you want to find your interval of convergence, where you want to have your radius of convergence multiple times, and then plug it into the Taylor series. So that's exactly what I'm going to do. Okay, so here, first one is I'm going to go ahead and solve for what is going to be f of 3. So f of 3, because at x equals to 3 is going to be my center. So at x equals to 3, we're going to have, it looks like it's 1 minus 3, so that's negative 2, so it's going to be negative 1/2. So that's my first part. Now I'm going to go ahead and solve for the derivative, f prime of x. F prime of x, that is going to be, looks like it's negative 1 over 1 minus x quantity squared. And because there's a negative in the inside, then that means that by chain rule, that becomes positive then. Okay, so that's my first derivative. Over there, I'm going to go ahead and solve for f prime of 3, just like I did before, or plug in x is equal to 3. So if I do so, looks like it's going to be positive in this case, which is going to be 1 over, looks like it's 4. But instead of writing 4, I'm going to go ahead and write it as 2 squared, just to see if I can actually see a pattern out of this. Okay. Now I'm going to go ahead and solve for the second derivative. And again, you're doing this as many times as it takes for you to be able to see the pattern there. Okay. My second derivative is going to be 1 over, it looks like I'm going to produce a negative 2 right here. And then we have 1 minus x cubed. And then you're going to also produce a negative 1 because of the chain rule. So that becomes 2 divided by 1 minus x to the third power. So now we're going to go ahead and plug in 3 for finding the second derivative there. So it's going to be equal to, let's see, the 2 is going to cancel in this case. Let me make sure everything is okay. There's negative, negative. Yes, that's right. And then so now we're going to have 2 divided by 2 to the third power negative. And there we go. Here it is. Because when you plug in 3, you're going to get 1 minus 3, which is negative 2, and raised to the third power. So that's where the negative is going to come from. All right. There you go. That sounds good. Okay. Now let's do it one more time. And hopefully by now we'll be able to see a pattern then. So for the third derivative, let's see. You're going to have a 3 that gets produced, negative 3. Times the 2 that was from there previously. And then we have 1 minus x to the fourth power, and we're going to multiply that by negative 1. So that's going to be my third derivative. And if I plug in 3 in this case, right, then on top, I notice the negatives cancels out. The top I might as well write as 3 factorial at this point because it seems like that's what it is, right? Negatives cancel out, so I don't have to worry about that. But the bottom part, you'll notice that we have negative 2 to the fourth power. So that's going to be negative 2 to the fourth power, which is going to be positive 2. So I feel like at this point, we probably do see a pattern over here. Focus on not the first part, but rather the second part, because that's what we really need to write our power series. Okay, this is the part that we need to write our power series. So here we have f of 3, f prime of 3, f double prime of 3, f triple prime of 3. So if I were to look at this as a general form, right, if I take the nth derivative at x equals to 3, according to what I have right there, it looks like the numerator is going to be the nth derivative, because each time you see on the top, you have 3 factorial, 2 factorial, 1 factorial, 0 factorial. That's probably why you want to write it this way, which corresponds to the number of times you take the derivative. And then all of that is going to be divided by the bottom. It looks like it's always going to be 2, but to be a little bit more specific, notice how it alternates from negative to positive to negative to positive. So I'd like to think it's going to be 2 and then raised to the certain power, and that power, it looks like it's 1 more than the derivative, so it's going to be 2 to the n plus 1. And finally, for that alternation part, we're going to go ahead and take this and multiply by negative 1 raised to the nth power. Check it just to make sure that it does work. When n is equal to 0, I don't get a negative, so that means I'm going to go ahead and put a plus 1 over there. So there it is. So that's going to be my nth derivative at x equals to 3. All right, so now we're going to go ahead and put it all together then, okay? So then that means that 1 over 1 minus x, right, the Taylor at x equals to 3 is going to be equal to the following then. So the first one is going to be equal to, looks like it's negative 1/2. Okay. And then the next part is going to be plus the first derivative at x equals to 3. So that's 1 factorial over 2 factorial, over 2 squared, and then multiplied by x minus 3. Okay. And then we also have for the next one, that's going to be minus, okay, minus 2 factorial over 2 to the third power. And if you remember in the Taylor series, there's also a divide by 2 factorial for that part. Okay, so don't forget that one. And then multiply by x minus 3 squared. Then the next part after that is going to be a plus. Looks like it's going to be 3 factorial divided by 2 to the 4th power. And then we also multiply by 1 over 3 factorial. Because again, remember, look over here, right? The Taylor series, there's a divide by 2 factorial, divide by 3 factorial, divide by 4 factorial. So that part needs to be applied also as well. And then, so let's see, the blue part, now it's going to be x minus 3 quantity cubed. And then minus and so on and so on and so on. Okay. Take this guy right here, clean it up, and then that will give you your Taylor series then. So that is going to be equal to negative 1/2. And then the next part, I guess we could just go ahead and write it as is. So it looks like it's going to be plus 1 factorial over 2 squared, and then x minus 3. And then for the second part, the factorials are going to cancel out. So all that's left is 1 over 2 cubed. So let's see. So that is going to give me 1 over 2 cubed. And then we have the x minus 3 quantity squared. The next part, the factorials again are going to cancel out. So then that leaves me with 1 over 2 to the 4th. And then we have minus x to the x minus 3 cubed. And I think the next part, if I'm looking at it correctly, should be minus, actually, because there's an alternation right here. Minus. And looking at the pattern that I have right here, it looks like the numerator is always going to be consistently 1 because the factorials on the top and the factorials on the bottom are going to cancel out. So that gives me probably going to be 1 over 2 to the 5th right here. And then this guy is going to be x minus 3 to the 4th power. And then plus and so on and so on and so on. When you write these terms, you have to make sure you write enough so then that way you can actually see the pattern. So all this right here, it looks like the pattern to me is going to be the summation starting at n is equal to 0 all the way into infinity. Looks like in the denominator, I have 2 to the power of n, where n is going to be the number of terms, but it looks like it's going to be 1 more than that. So that's going to be n plus 1. And then the top part, there's a 1 right there. And it looks like also I need to apply the alternation of the positive and negative. So let's go and change that 2 on the bottom to a negative 2. So this guy right here is going to be then negative 2 raised to the power of n plus 1. Multiply by x minus 3 raised to the power of, looks like in this case, is going to be n then. So right there, that is going to be my Taylor series at x equals to 3 for the function 1 over 1 minus x then. Okay, and if you want to find out what is your radius of convergence, then that's where you're going to have to do the ratio test in order to figure out where is it going to, how far out you can actually go, how far out in each direction can you actually go in order to use this Taylor series. So here, let me just kind of finish that off. So first, I'm going to go ahead and say limit as n approaches towards infinity of the absolute value of this sequence that I have. So 1 over negative 2 raised to the power of n plus 1 multiplied by x minus 3 raised to the nth power. So that's going to be my current term, which is actually, I need something else. I need the next term. So that's going to be n plus 2, and there's going to be n plus 1. And then all of that is going to be divided by the current term, which is 1 over negative 2 to the power of n plus 1 times x minus 3 raised to the n power. We need to make sure that this guy is going to be less than 1. So clean up your math over here. Let's see what happens. The absolute value will take care of the negative part, which alternates, so that's good. So limit as n approaches towards infinity. For the first part, I am going to, looks like if I were to cancel some stuff out, it looks like it's just going to be 1/2 for these two guys over here. So hopefully that is going to be my case right here, because it's technically -1/2, but again, the absolute value will get rid of it. And on the other part over here, that's going to leave me with x minus 3, and then there's going to be no exponent, well, exponent of 1, and that is supposed to be less than 1 then. Okay, so now we can go ahead and solve for x over here, because as n approaches towards infinity, looks like all those terms are going to cancel out. All we have left is just the x part, so that's good. So just like before, we're going to go ahead and solve for x to get our interval of convergence. So x minus 3 is going to be absolute value is going to be less than 2, because I'm going to multiply that to the other side. So -2 is less than x minus 3 is less than 2 over here. And then now I'm going to add 3 to everything. So that means it's 1 is less than x is going to be less than 5. So right there, that is your radius of convergence. And finally, because, you know, we need to make this even more complicated, we got to check the endpoints to see, are they also going to be included or not. So throwing it in just to see what happened. When x is equal to 1, what I'm going to get is the summation of n is equal to 0 all the way to infinity of 1 over -2 to the n plus 1 multiplied by 1 plugged in. I'm going to get -2 to the power of n. So let's see, if we were to clean that up, that is going to give me the summation n is equal to 0 to infinity. The bottom part and the top part looks like it's going to cancel, and so all that is left is going to be 1 over -2. So since you're adding a whole bunch of -2, then therefore this is going to be divergent then, because there's no way for that to be equal to a certain sum. Whereas when x is equal to 5, then we get the summation of 1 over -2 to the n plus 1 multiplied by 2 to the n. And let's see, in this case, what will happen there is we can kind of rewrite this just to make our life a little bit easier. Let's write the bottom part as 2 to the n plus 1 multiplied by -1 to the n plus 1. So then that way we can isolate and see what gets canceled. The top, the 2 to the n, and the bottom, the 2 to the n, they cancel out, leaving you with just a 2. And then we have -1 to the power of n minus n plus 1 over here. So when you get that, that is now going to be equal to, looks like it's going to be 1/2 minus 1/2, and then plus 1/2. And it looks like you're basically adding a bunch of 1/2 and -1/2. So therefore, this is also going to be divergent. So in conclusion, then your final radius of convergence, or your interval of convergence, is going to be just strictly from 1 to 5 then. Okay. All right. Thank you so much for watching. I know there was a derivation of sine, but I'll save that for next time. Okay. All right. Talk to you later. Bye-bye.